Here's a test. Ask an AI, what is the boiling point of water at sea level? It'll tell you, correctly, 100 degrees Celsius. Now ask it, who won the 2031 World Cup? It'll answer just as confidently. Same tone, same authority, same fluent delivery. And it'll be wrong. Or it'll be making something up. But you won't know which just from the way it sounds, because it doesn't sound different when it's fabricating. That's the deep problem. Not that AI makes mistakes. Everything makes mistakes. But that AI makes mistakes in a way that's indistinguishable on the surface from AI being completely correct. This is the limitation that practitioners and stakeholders most frequently underestimate, and most frequently get burned by. Not because they didn't know AI has limits, but because they never fully internalized what those limits actually look like, where exactly they appear, and why the system can't detect them from the inside. This lesson is about building a precise, honest map of where AI reliability breaks down. Not a vague AI isn't always right disclaimer, but a specific, technically grounded understanding of the three primary failure modes: hallucinations, knowledge cutoffs, and reasoning gaps. And then we'll go one step further. We'll talk about how to communicate those limits clearly and honestly to the people who depend on your work: clients, colleagues, stakeholders who may not have the technical background to know when to trust AI output and when to verify it. This is the expertise that makes you genuinely valuable as a practitioner. Not just knowing how to get good outputs, but knowing exactly where outputs go unreliable, and building that awareness into everything you deliver. The word hallucination is vivid, but it's slightly misleading. It implies the model is confused, dreaming, seeing something that isn't there. What's actually happening is more mundane and more structural, and understanding the mechanism makes you a much better practitioner. Here's the root cause. An LLM doesn't have a fact-checking module. It doesn't have an internal database it searches before responding. What it has is a probability engine, a learned ability to predict the most statistically plausible next token given everything that came before it. Most of the time, most statistically plausible and correct overlap. When you ask about well-established facts that appeared in enormous quantities in the training data, the most likely next tokens are the accurate ones. The model has seen this pattern 10,000 times. It produces the right answer as a natural statistical output. But here's where it goes wrong. When the model reaches a question where it doesn't have strong statistical patterns to draw from, niche topics, recent events, obscure details, domain-specific facts, it doesn't stop. It doesn't say, I don't have reliable data on this. It keeps generating. It fills the gap with the most plausible-sounding continuation given the context, which often looks like a specific name, a credible-sounding citation, a confident statistic. It's doing what it was built to do, completing the sequence. The problem is that completion and accuracy are mathematically separate objectives. Here's the most important thing to understand about when hallucinations occur. They cluster in very specific situations. First, when you ask about names, citations, statistics, or dates, these require precision, exact strings of characters. And when the exact string isn't well represented in training data, the model interpolates towards something plausible. The result is a name that sounds real but isn't, a citation that looks real but links to nothing, a statistic that seems reasonable but was never actually measured. Second, when you ask about events near the model's knowledge cutoff, the training data gets sparse as it approaches the cutoff date. Sparse data means weaker statistical patterns. Weaker patterns mean higher error rates. Third, when you ask for multi-step reasoning where each step builds on the previous one, if the model makes a small error early in the chain, which it might because it makes each step by statistical prediction, not logical deduction, that error compounds through subsequent steps. By the end, the conclusion can be completely detached from reality. Techniques like chain of thought prompting help with this third category because they force the model to make its reasoning steps visible and explicit. When reasoning is explicit, errors are easier to catch, by the model in self-critique mode or by a human reviewer. But they don't eliminate hallucinations. They make them more catchable. The model doesn't know when it's hallucinating. You have to know when to expect it and verify accordingly. Hallucinations can happen with any topic, but they become nearly guaranteed once you step past a particular date. This is the knowledge cutoff problem, and it's one of the most consistently misunderstood aspects of working with language models. Every large language model has a training cutoff, a date beyond which it has no knowledge of what happened in the world. Events after that date didn't exist when the model was trained. New research, new laws, new products, new political events, new scientific consensus, new cultural shifts. None of it is in the model's weights. Think about what this means in practice. If you're using a model with a cutoff from 18 months ago, you're having a conversation with something that thinks the landscape of that time period is current. It doesn't know what's changed. And critically, it doesn't always know what it doesn't know. It can confuse, "I don't have data on this," with "this hasn't happened." The model isn't lying when it gives you outdated information. It's telling you the most accurate thing it knows. And what it knows has an expiration date you need to account for. Here's the practical breakdown. 3 categories of tasks are most exposed to knowledge cutoff failures: current events and recent developments, anything that happened after the training cutoff, political changes, market developments, new research publications, product releases, regulatory changes, public health updates. All of this is outside the model's dataset. Rapidly evolving domains. Even facts that existed before the cutoff can be outdated in fields that change quickly. Drug approval status, security vulnerability patch logs, best practices in software development, legal precedent in active areas of law. The model might have accurate information from 18 months ago that is now outdated, and it will deliver that information with the same confidence as it delivers timeless facts. And third, the model's own capabilities and the AI field itself. AI is evolving faster than almost any other domain. A model's knowledge of other AI models, tools, benchmarks, and research is almost certainly incomplete even at the time it was trained, and it's almost certainly out of date by the time you're using it. The mitigation strategies are practical. Use Retrieval Augmented Generation, RAG, to supply the model with current information via its context window. Use external tools and APIs for real-time data when the application requires it. And disclose the knowledge cutoff to stakeholders explicitly whenever AI-generated content will be used for time-sensitive decisions. The cutoff isn't a design failure. It's an architectural characteristic. It becomes a problem only when you or your stakeholders treat the model as if it has live access to current information, which it doesn't. Beyond hallucinations and cutoffs, there's a third category of known failure: reasoning tasks that language models consistently underperform on. Not because of missing data, not because of architectural cutoffs, but because of fundamental properties of how the model processes information. The most important distinction here is the one between pattern matching and genuine reasoning. Language models are extraordinarily good at pattern matching, recognizing when a new situation resembles a well-represented pattern in their training data and applying the learned resolution. This looks like reasoning. For a huge range of tasks, it produces reasoning quality outputs. But for a specific subset of tasks, pattern matching breaks down, and you need something that looks more like systematic logical deduction. And the model's default mode doesn't provide that. Which tasks? Let's be specific. Multi-step arithmetic and complex mathematics. The model produces plausible-looking math, but each step is generated probabilistically, and errors compound. For anything beyond basic single-step calculations, AI math should always be verified. Tasks requiring causal reasoning across implicit context. If problem A caused condition B, which enabled event C, but none of that causal chain was explicitly stated, just implied, the model often misses or misrepresents it. It sees the surface pattern without reliably inferring the underlying mechanism. Long horizon tasks where actions taken early constrain options available later. The model tends to optimize locally, making each next step seem reasonable, without reliably holding the full constraint structure of a complex, interdependent problem in view. And tasks involving logical negation and exception-heavy rules. Natural language is ambiguous about not and except in ways that the model's probability-based processing doesn't always resolve correctly. None of this means avoid using AI on these tasks. It means use AI with eyes open, with verification designed in, and with honest expectations about where you'll need to check its work. Understanding limitations is the internal half of the work. The external half, and often the harder half, is communicating those limitations clearly to people who may not have the technical background to model them accurately on their own. Here's the gap that creates the most risk in real-world deployments. A prompt engineer or developer fully understands the AI system's limitations. They know about hallucination risk. They know about the knowledge cutoff. They know which tasks are unreliable. But the stakeholders, clients, or end users who depend on the system's outputs don't. And because AI outputs are fluent, authoritative-sounding, and well-formatted, people without technical context tend to overtrust them. The same quality that makes AI useful, it sounds credible, makes it dangerous when that credibility isn't warranted. Your job is to close that gap, not with a one-page disclaimer buried in terms of service, with clear, plain language disclosure built into how you present and document AI-assisted work. Here's a practical disclosure protocol. 3 things that should be communicated to any stakeholder relying on AI outputs for consequential decisions. First, disclose the fundamental mechanism. This system predicts the most likely response based on patterns in its training data. It does not retrieve facts from a verified database. It can generate plausible-sounding content that is factually incorrect, and it cannot always detect when it has done so. That sentence, said clearly, resets stakeholder expectations more effectively than any amount of vague "AI can make mistakes" boilerplate, because it explains why, and understanding the why makes the limitation concrete. Second, specify the knowledge cutoff. The model's training data extends to approximately date. Information about events after that date, recent regulatory changes, new research publications, or current market conditions may be missing or incorrect. For time-sensitive applications, outputs must be verified against current authoritative sources. Be specific about the period, not just AI has limited knowledge. Third, mandate expert verification for high-stakes outputs. All outputs produced by this system that will inform medical, legal, financial, or safety-critical decisions must be reviewed and validated by a qualified subject matter expert before being acted upon. This is about appropriate division of responsibility.